LB-274, lab number 3. Our main idea was how spectroscopy is used to identify substances and what is the physics involved. It was found that our unknown was likely Laperouse dye. Our materials included cuvettes with an unknown orange dye, a fluorescent dye, a spectrophotometer, a flashlight, and tape used to keep our experiment in place to ensure consistent data. Absorbance spectroscopy uses radiation shot out from a spectrometer to measure the light absorbed by the sample. In order to do this, it measures the intensity of the waves before and after the light hits the sample, and the resulting graph is calculated using log 10 of initial intensity divided by the resulting intensity. Since different materials absorb different wavelengths, this can help us identify substances like contaminants in a water supply or pollutants in the air. First, we used water in a cuvette as a control. We secured the flashlight and spectrophotometer with tape and dimmed the lights. It's important for the room to be dark so we don't get extraneous data from the surrounding light. The cuvette was placed between the flashlight and the spectrophotometer, and the spectra was measured on a computer. This was repeated with the unknown dye and the fluorescent dye. The fluorescent dye was made sure to be placed at a 90-degree angle to ensure most exact results. Excel was used to create transmission and absorption spectra for both dyes as well as an emission spectrum.
The two major physics concepts involved here are fluorescence and absorption for spectroscopy, and those have to do with what happens when incident light hits a molecule and electrons become excited. Because these aren't quantized as much as single atoms because of vibrational modes and complexities, they sort of form different energy well states. So there's a variety of wavelengths that can be absorbed as they sort of roll around in those modes to go up to the U star state and then fall back down. There's not always a straight line path back, so energy is still conserved. Energy just may be lost as heat or vibration, which is why a different wavelength may be emitted in the case of fluorescence. Absorbance, there's still this shift, but there's not as much of a drastic shift back down. Usually it's more of a vibrational heat movement release and not a fluorescent emission. And then Beer's law quantifies this absorbance with path length, concentration, and something specific to each substance, which is epsilon. And you can sort of see to the right a plot we made in ChemLab to do a similar thing relating concentration and absorbance. Uses for fluorescence spectroscopy include really interesting medical applications, like the identification of tumor and cancerous cells as opposed to normal cells, which sort of have different profiles. The top graph represents the water blank, so just the wavelengths and the intensities that would make it through the water in the cuvette without dye. And then the middle graph shows the transmittance of the wavelengths that made it through once the dye was in place. So by subtracting those, we get the bottom graph, the intensities at the wavelengths that were absorbed by the dye. And we were able to identify that the orange dye was a Lapidus dye based on the similar peaking pattern to what was provided in the lab manual. And then we were able to calculate concentrations using Beer's law. So the calculations are right here, basically by taking the logarithm of the ratios of the initial intensity, so what went through the water, and the final intensity, so it went through the dye, and then dividing that by the path length and the constant associated with the dye we identified, we're able to get the concentrations as found below by averaging a bunch of values.
We also found the fluorescent transmission spectrum by using the spectrophotometer. The graph shows intensity versus wavelength of the fluorescent dye. To find the fluorescein absorption spectrum, we subtract the fluorescein transmission spectrum from the water transmission spectrum that we already found. The graph shown here is the fluorescein emission spectrum. This graph measures the amount of light that is fluoresced off. This fluorescence corresponds to when the electrons fall from the excited state back to the ground state, which gives off energy in the form of wavelengths of fluorescence. Our calculated absorption spectra for fluorescein matches the known fluorescein absorption spectra on the right that is given in the lab manual. The fluorescein emission spectrum we calculated also matches the known emission spectra. This shows how scientists can determine which molecule is present. After our analysis, using the spectrophotometer, we determined that the unknown dye was the Lapidus dye. We did this by matching the absorption spectra. In order to confirm these results, there should be another chemical test taken. We also found that the absorption and fluorescence spectra matched that of the fluorescein. Beer's law can determine concentration from absorbance and path length. Our average concentration of the unknown dye is 2.26 times 10 to the negative 6 molarity, and our fluorescein concentration is 1.71 times 10 to the negative 6 molarity. The fluorescence and absorbance of materials can be used for identification. Beer's law applies absorbance to identify substances. Our potential sources of error are that the fluorescence was probed from this side, so a different intensity could have been found. Also, tests were not performed in complete darkness, which may have skewed our spectra.